Hi, I'm Mr. Miller, and this is a lesson on the remainder theorem. So, in order to understand the remainder theorem, it's helpful to look at some specific numerical examples. So, let's say, for instance, that I was trying to do 31 divided by 2. I could do a long division to see how many times 2 would divide into 31, and it would look like this. So I would ask myself, first of all, how many times does 2 go into 3? And say, okay, well, it goes in once. 1 times 2 is 2. And if I subtract, I will have 1 left over. Now I bring down the 1, and I ask myself, how many times does 2 go into 11? And it's 5 times 2 gives me 10, and I have 1 left over. So here's what I have. 31 divided by 2 is 15, and the remainder is 1 out of 2. So most people write this as just 15 and a half, but of course it is 15 plus 1 divided by 2. And so the remainder is what you'll see here. Right? This is the remainder. And it's what you put up here over what you call the divisor. This is the divisor. This is the thing that we were dividing by was 2. Okay, so just to get the terminology complete here, the 31 is what you would call the dividend. The 2 is what you would call the divisor. And the 15 is what you would call the quotient. And then again, you've got the remainder, which is over the divisor. All right. So now that we've gone over that numerical example, we can look at how does this play out when we're doing division with polynomials. So let's suppose that we've got p of x, which is being divided by the binomial x minus a, where a is just some integer. Then the division can be represented in this way. P of x divided by x minus a equals the quotient plus the remainder over x minus a. So it's kind of like when we had here 31 divided by 2 gave us 15 with a remainder of 1 out of 2. So again, in this situation, p is the polynomial, it's the dividend. The x minus a, this is the divisor. Q of x, that's the quotient, and r is going to be the remainder. Now I should mention there is one other form that in this example we're looking at using, and let me just explain that in terms of the numbers. So I think it's helpful to understand that in terms of the numbers. What we're also saying is that the value of 31 is equivalent to 2 times 15 is 30 plus 1. So hopefully you can see where all of these parts go. So this was our dividend, was 31. The divisor, when you multiply by the quotient, gives you 30. And then there's, if you add on the remainder, you get the full value of 31. So now back to this example, we're going to look at dividing this polynomial, it's a cubic polynomial, by x minus 3. We're going to do a long division, and then I'm going to show you a quicker way, which is called synthetic division. We're going to express this division in the form p of x over x minus a equals q of x plus r over x minus a. So again, p is the polynomial, x minus a is the binomial divisor, q is the quotient, and r is the remainder. And we'll also put it into this other form. Now, when we're dividing by a variable, we have to make sure that variable we're dividing by doesn't end up being 0, because that can make the whole thing undefined. So there are restrictions on the variable, and I'll just point it out in this way, that if you think about division, most people understand that 8 divided by 4 is equal to 2 because they understand that 2 is the number that when you multiply by 4, you get 8. But then the question becomes, what happens when you're trying to divide by 0? You get what? Well, some people will answer, oh, it's 0, it's 8, it's -8, it's 1, it's -1, it's, I don't know. So whatever the answer is to this question, it would have to be the answer because when you take that number and you multiply by 0, you get 8. So what's the number that when you multiply by 0, you get 8? Let's see. Well, some people say the answer here is 0. Well, no, 0 times 0 is 0. Oh, the answer is 8. No, 8 times 0 is 0. Oh, the answer is -8. Well, -8 times 0 is also 0. And how about 1? Well, no, 1 times 0 is 0. And then you say, wait a minute, there is no number that when I multiply by 0, I get 8. So that's why mathematicians say that this thing is called undefined. So long story short, you're not allowed to divide by 0, not even if you're Chuck Norris, okay? And in fact, if you're dividing by x minus a, you want that x minus a not to be 0 as well. So we'll talk about the restrictions afterwards. So let's get down to the division. We're dividing x minus 3 into this cubic. And in order to do the division, first of all, we kind of like with the 31, we need to knock off things from left to right. So we'd like to be able to subtract away the 6x cubed. Well, what do I need to put up here so that when I multiply by x, I get 6x cubed? And of course, that's 6x squared, right? 6x squared, when you multiply it by x, you get 6x cubed. And 6x squared times -3 gives you -18x squared. Now we have to do a subtraction to see what's left over. And it's 13x squared. So the next step is I need to decide what to put here that when I multiply it by x, I'm going to get 13x squared. Oh, and by the way, we need to bring down that positive x term. So as I mentioned, I need to figure out something I can put here that when I multiply it by x, I get 13x squared. That would be 13x. 13x times x is 13x squared. When I do 13x times -3, that gives me -39x. And now if I subtract away, here's what I have left over, is 40x. And now I bring down the -1. And now the last term, I need to figure out what I put here so that when I multiply by x, I get 40x. Well, of course, that's just 40. So 40 times x is 40x, 40 times -3, -120. Subtract away, here's what I have left over is 119. So the division is done, but of course this kind of takes up a lot of space and time, and it involves subtracting negatives and all kinds of nasty business. So I'd prefer to have a way that is more compact, easier to do, and less likely for me to make mistakes. So here's what I'm going to do. Instead of using the -3, I'm going to use +3. Okay, so already I'm involving opposites because you know that subtracting can be done by adding the opposite. So that's kind of the idea that I'm using here by switching the -3 to a +3. I've copied the coefficients of the polynomial, so the 6x cubed, the -5x squared, the +1x, and the -1, all those coefficients are there. I'm going to leave some space for the quotient to go down here, and then some other work that shows up here, and then I'm going to have the remainder show up over there. So step 1 is I'm going to copy down the 6, and this is the 6x squared, just like we have a 6x squared here. Now think about what the 6 did. It multiplied the -3 to get -18x squared. So likewise, I'm going to do 6 times 3 is 18 and put it here. But because we have a +18, now I don't have to subtract a negative. Now I get to add because I'm adding the opposite. It is the equivalent but it's much easier to do an addition than it is a subtraction. So 18 plus -5 gives me 13. And now notice that that 13 is a 13x, which is the same as a 13x there. And now I'm going to do 13 times 3 is going to give me 39 here, just like 13 times -3 gave me -39x here. And instead of subtracting a negative, I get to add the opposite, which is easier. 1 plus 39 is 40. Notice how the quotient here has a constant term of 40, just like we have there. And now I do 40 times 3 is 120. And then I get to add these two together rather than having to subtract. I can add the opposite. And here's what I get for a remainder, still 119. So same thing, but notice that this is much more compact. Plus, it involves addition instead of subtraction, and I'm better at addition. I tend to make less mistakes that way. So at this point, I'm ready to write my division in those two forms. So first of all, the cubic polynomial, when we divide by x minus 3, here's what we get. We get 6x squared plus 13x plus 40 with a remainder of 119 out of x minus 3. And that's one of the forms. The other form is that cubic polynomial can be written as x minus 3 times 6x squared plus 13x plus 40 plus the remainder of 119. As far as restrictions go, there's just one restriction, which is the x minus 3 can't be 0. Again, you don't want to be dividing by something that's 0 because it'll be undefined. So if x minus 3 can't be 0, then that means x is not equal to 3. Now, the remainder theorem states that when a polynomial p of x is divided by the binomial x minus a, where a is an integer, the remainder is p at a. So from the previous example, right, we had this polynomial, the 6x cubed minus 5x squared plus x minus 1 that we were dividing by x minus 3. Here's another way that you can get the remainder. You can take that polynomial and evaluate it at 3. So 6x cubed, 6 times 3 cubed, minus 5 times 3 squared, plus 3 minus 1. And I get a remainder of 119. So if my goal was to get the remainder, I could just evaluate the polynomial at, again, because I'm dividing by x minus 3, I evaluate the polynomial at 3, and this is my remainder. So likewise, you could use the remainder theorem to determine the remainder when this particular polynomial is divided by x plus 2. And then we're going to verify that using synthetic division. And you can do long division if you want to as well, but who wants to do that? All right, so I'm going to evaluate the polynomial at -2. Notice that it says if you're dividing by x minus a, well, this is like x take away -2. So it's -2 for a, and I substitute that into the polynomial. And if I calculate the value of this, I get -13. Now, if I do synthetic division, here's what it looks like. So I take the opposite, -2 here, and I put coefficients of the polynomial that I'm dividing into. So it's 1x cubed, and there's a 0 because there's 0x squared. So you do have to keep that placeholder 0 for the x squared term, even if it's not there. Plus we've got 3x, and then plus we've got a constant term of 1. I'm going to leave some room for my quotient and then the remainder in the bottom right-hand corner. So now I'm going to copy down the 1. 1 times -2 is -2. Add those two things together, multiply by -2, add the 3 and the 4, multiply by -2, add those two together. Here's the remainder, it's -13. So in both cases, I get the same remainder. Now, for those of you taking Pre-Calculus 12 with me, if you would like to see another example, you could take a look at example number 2 on page 121 of your textbook. Otherwise, hopefully this lesson has been informative, and thank you for watching. Have a great day.